Okay, let's review rate laws. We are going to do it for a couple of reactions. We'll start with the simple one, which is a reactant A gets irreversibly converted into product P with a rate constant of K. So this is rate constant. How do we determine the rate of this reaction? The rate or velocity would be equal to the change of product concentration, accumulation of product over time. And that will be the same so as product accumulates, reactant needs to be consumed with the same rate to ensure conversion of the reactant into product. So the velocity of product consumption should be the same as the velocity of product accumulation, but with a negative sign because product concentration gets increased over time and reactant concentration gets decreased. So it will be equal to minus a change in the reactant concentration over time. And at the same time, velocity is proportional to the reactant concentration because the more reactant we add, the faster is the reaction. So we have this proportionality coefficient, which is equal to the rate constant multiplied by the reactant concentration. And because there is no power here, right, it's just the power is equal 1, we called such reaction a first order reaction. So we are going to now derive a first order rate law. Let's focus just on this portion right here. So if you do so, we can rearrange and solve this equation. So we are going to group all terms that have a concentration of the reactant in them in the left part of the equation, and all terms that don't have concentration of the reactant in the right part of the equation. So now it doesn't work. It doesn't cooperate with me. Okay. So change in concentration of the reactant over this concentration of the reactant equals to minus, because we need to transfer it right here, K by dt. Now we take a logarithm of the left part and the right part of the equation, and we need to put some, because when we, logarithm, integral, of course. When we integrate a function from certain starting point to a certain end point. And the starting point is, of course, the beginning of the reaction, so the time is 0, and the end point is some time point, right? We don't know any time point, actually. And at 0 time point, the reactant hasn't started been converted into product, so its concentration is equal to whatever we started with. And at time t, we have just the reactant concentration. So when we integrate, that will be equal to the natural logarithm of the concentration of the reactant less the natural logarithm for the reactant concentration at 0 time point. And on that right part, it will be minus K, and here you will have T minus the starting point 0, so we can simply erase that second term, right, because it doesn't make any difference. So that's our equation. Now we can simplify it by having just logarithm of the reactant concentration on the left part of the equation, and the logarithm of the starting concentration will move to the right part, minus kT. T is the time, K is the rate constant. And we can simplify it even further by raising everything to the exponent. So we kind of have exponent here and there, right? And we can simplify exponent of the natural logarithm of A, because the base here is the same as here. We have just, concentration, right? And on that side, we have e to the power of natural logarithm of starting concentration by e to the power of kt. And that is equal to, actually, let me move it right here because I want to write it down over there for the rate law. So we have concentration equal to the initial concentration by e to the power minus kt. Now, if we plot the concentration as a function of time, we have exponential decrease as expected from some initial point, which is just the initial concentration, and it drops, of course, kind of like that, right? Drops like that. And here we have time from 0 to any time point. But it will be interesting to know at what time point we have initial concentration decreased twofold, right? So drop twofold. So this time is called half-life, and it is designated by either t 1/2 or Greek letter tau. So this is half-life of the reaction. So how to determine that half-life? For that, we need to plug this concentration into our rate law. And in this case, T translates into the tau, half-life, right? And we can solve this reaction for tau, for that unknown. That would be equal to 1/2. And on the right part of the equation will be e to the power of minus k tau, or 2 equal to e to the power of k tau. And so to get tau, we need to take logarithm from both parts of the equation. And that would be equal to just k tau. And so tau will be equal to logarithm 2 over k. So you see that half-life depends just on the rate constant. It doesn't depend on the concentration of the reactant. Another thing that I wanted to point out would be wanted to comment on something here. So it's kind of inconvenient to use just that exponential decay to determine k, because here, in order to calculate tau, for example, you need to know the rate constant, but you don't know that. You need to experimentally determine that. And the best way to determine it experimentally would be to test the rate, velocity, right, of the reaction, or pretty much test how concentration of the reactant decreases over time. And we can use, actually, we can go back to that equation and we can rearrange it like that, right? As we rearranged it before, but I already changed it into the exponent. So this is a linear equation. So if this is our y, this is our x, right? Because we change time and we measure concentration at every time point, we can easily take logarithm, right? So here we will have our y-intercept, but we are interested in k, and that's our slope. So we expect, if we just draw, if we just graph logarithm of product concentration as a function of time, we expect to start with this initial point, which is equal to natural logarithm of the starting reactant concentration, and we expect it to drop like that linearly, right? K here, K is the slope. And of course, you can always calculate the tau, which is the time at which the concentration of the reactant is equal to half of the initial.